Hey everybody, right back into it this week, guys. I usually start with a pretty long-winded intro where we discuss the definitions of design concepts and I go off on various tangents, but we got that taken care of in last week's video as far as artificial intelligence for games is concerned. So I wanted to just jump right in on the planning and execution phase of our video this week. If you didn't watch last week's video and are still sketchy on what AI really is, just click the previous video link in the description. It's discussed at characteristic length in that one. So, with an unprecedented lack of further ado, part 2 of my bit on zombie AI, or ridiculously undercomplicated AI. We're talking aggro today. What is aggro? If you play MMOs, or honestly most games with hostile AI, you'll start to get a feel for how far a monster has to be away from you before it'll suddenly turn and start getting all up in your grill. What that is an example of your character triggering aggro, or crossing the event horizon to an enemy's detection range, where the game tells the monster that it's go time. That's what we're going to be doing today. As usual, there are shortcut links in the description, so you can skip this part if you want to get straight to those sweet nodes and wires, but first, planning. So we know how aggro should work. You get within a certain distance of a creature and it reacts. I'm going to go over not one but two ways to accomplish this, which I'm going to term the hacky way and the fancy and ultimately more useful way. The hackiest way to do this is to abuse Unreal 4's collision query overlap function, which basically says that you can have a component of an actor extended outwards, invisible to the player, which has no physical presence, but which triggers an event anytime another actor enters or exits its geometry. You can also dynamically call an event to get an array of actors that are currently overlapping its geometry and apply some logic to those. It works, but it's really inelegant and not very extensible. By which I mean its uses can be a little bit limited. Not only that, but fine-tuning can get that much more difficult when you're dealing with characters that need more than a few components. Instead, I'd like to continue our foray into function creation by building ourselves an aggro mechanic using a function that we can then apply in a number of other useful situations. As a matter of fact, this is a development theme that I think deserves to be introduced and stressed repeatedly to anyone that's interested in game development as a hobby or as a career, especially when you want to work in design. You're going to find over the course of your lifetime creating games that there's going to be a number of things that you'll have to do over and over again in various situations. One of the most important jobs for a game designer that deals with game mechanics, like myself, is to identify those frequently repeated tasks and know when to turn one of those into a function that you can call regularly. This is going to be one such function. I can think off the top of my head at least 5 cases in which we're going to want to get a reference to another actor within a certain distance based on a specific criteria. Hell, based on which of the group of characters is closest in general. Of course this applies to determining a target for aggro, but how about determining a character to interact with, or finding the nearest tool to pick up to do a job, the closest valid place to sit down, the nearest group of resources to gather, and the list goes on. We can make the function extensible by adding other criteria as well, like finding the target with the highest or lowest of a certain stat, or something that requires even more in-depth logic, like determining which character within the defined range they consider the most dangerous. Since this sort of functionality will ultimately be very useful to us, we should make a function in our AI character parent class, the AI-based template, that we can then call from any of its child classes anytime we might have a use for it. If we decide we need more criteria to search from, we can totally add it afterwards as well. I'd even go so far as to say that this should be a function of most games that include artificial intelligence. So why isn't it, you might wonder? Well, the problem with predefined functions like this is that it's impossible for the creators of an engine to ever really factor in and anticipate every possible scenario in which you'll want to use a function. For things like simple movement or actors overlapping others and triggering events, those are things that you would almost always expect to see, but what if there was a function to get the nearest actor but you wanted to use a different criteria? Either the engine's creators would have to anticipate and extend the base function far beyond the scope that any one function should go, or you have to do it yourself. In this case, since it's functionality that's going to have to be specialized to our own needs, even though it's fundamental functionality, it's one of those latter cases. I could easily do an entire episode about functions, how you should go about defining them and why you need them, and why any programmer you work with will be much happier to work to your specifications for understanding how they work. But I've covered the basics for now. Even my attempts at brevity last for minutes at a time, so let's just go ahead and move on. So Aggro is a group of discrete functions. First, let's tackle searching for a valid target to create a reference to. Before we start with the function though, I'd like to create what's called an enumeration, or an Enum blueprint. We can do this very easily by right-clicking our content browser, selecting Blueprints, and Enumeration. For those of you out there who are running in old versions of Unreal, this used to be in the miscellaneous group. They've moved it to Blueprints fairly recently. What an enum is basically a predefined text-based list of terms that we intend to use within functions or events. It sort of takes the place of another, more broad variable, like an integer, which again is a whole number, or a string, which is a free-form block of text. We could easily use anything we wanted as a variable for defining a switch, but the major benefit of an enum is twofold. It's easy to make use of, since we define each possible value ourselves, and it's safe, as it's much more difficult to call incorrectly. Just today at work, I was debugging an issue with some code that ultimately came down to me misdefining a string in some of my old script that, by all rights, should have been an enum. The enum I'd like to define right now will be a list of possible criteria for our search. I'm going to name it eTargetCriteria. The E at the beginning basically just tells us that it's an enum, for when I have to search for it later. File naming conventions and coding standards are a whole different episode, so I'm just going to gloss over that for now, but just keep in mind that we're going to be using some interesting prefixes when we're naming things from here on out. Now let's go ahead and open up our enum and take a look inside. As you can see, it's pretty empty in here. As I said before, it's basically just a list of terms in text that we'll want to reference later. I'll show you toward the end of the video why this is the best thing to have here, but for the moment let's just define a few possible criteria. We can always come back and add or remove as needed. For now we want to define closest, obviously, as well as, let's say, most health and least health. We're doing this just to have something for reference. These can really be anything. What's important is that they're understandable. We'll be using these in a moment, so let's save it, and then we'll close the enum and go to the AI-based template blueprint. Now let's create a new function. I'm going to name it getBestTarget, since it's going to be used to find one target that most closely matches the criteria that we set forth. Now that we're in the function, we'll want to define what we want to have as inputs for criteria, and what we want the function to output for use after it's done. For our inputs, for the moment, let's create an actor class reference and call it classDefined, a float, which we'll call searchRadius, and the eTargetCriteria that we just defined, called, imaginatively, searchCriteria. For outputs, we're going to want a reference to an actor, which we'll call bestTarget, which will be the actor that we ultimately decide on based on our search criteria, and a boolean called targetExists, which is basically just a clean way for us to verify whether there's something to reference or not, so we don't go trying to apply functions or events to something that doesn't exist, and then start throwing a bunch of null references and end up with an output log that's cluttered up with red lines of text. For variables, we're first going to want to create a float called maxRange. This is going to be a direct reference to our search radius that we can more cleanly use inside the function. We'll also want to create an actor array, which we'll call validActorArray, which will populate with a full list of all the possible actors that we'll search from later. There will be more variables added as we go, but let's get to them when we need them. The first thing we're going to do from our execution pin is to set our max range variable. It'll be as simple as pulling a wire from our search radius pin into the variable. It's going to be used a few times through the function, so we want to set it nice and early. The second thing we'll want is what's called a sequence node. This awesome node allows us to tell the engine to perform one chain of actions, and then when it's done, or when it reaches a natural breaking point, instead of making a huge long chain, it'll start executing another chain. In this case, it's mostly just housekeeping, but keeping blueprints clean is an art form. Learn your flow control tools early, and your life is going to be a lot easier. So let's pull a pin out nice and high from the then 0 output, and create a MultiSphereTraceForObjects node. This serves the purpose of the actor component we talked about at the beginning of the video, but it's much less in the way. It temporarily creates a sphere and then checks inside it for hits. This node needs a few inputs. It needs a start point, which is the center point of the sphere, and an end point, which basically allows it to actually create an elongated capsule-shaped sphere. Both of these will be centered on the actor calling the function, so let's get the AI's capsule component, and from there, get world location, which gets the vector data saying exactly where in the game world the actor currently is. We'll pull a wire from the return value and attach it to the start point. I'd love to just attach it directly to the endpoint as well, but Unreal doesn't like that, so we'll need to add at least a little volume to the sphere by adding a little to the z-axis of the vector using an add vector node. Easy. We also have to tell the game what to look for and how far away from the actor to look, so let's get a reference to our max range variable and wire it into the radius pin. The object types is asking for an enum array. Unreal automatically assumes and creates a few enums for you, one of which being a list of object types, which you can define in the project settings. We'll drag a wire out from the arrays pin to the left and click Make Array. We could also make a variable for this, but this is completely functional for what we want and we're not going to need it elsewhere. We only really need to search for pawn now. That will return just about anything that we could possibly want. We can leave the rest as defaults. We could define more things in here, but there's really no need. Instead, let's continue forward. For the sake of cleanliness, let's create a branch here from the return value pin. This tells us whether any actors were found. If false, we want to abort the function now and tell the game that there's nothing at all that we could use, and save ourselves some computing power. We'll wire in a return node here, and also wire the return value to our target exists pin. But that's the unfun result, of course. Instead, let's move on to what happens if there is something, or a group of somethings. As it returns an array of hit results, we'll need to create a for each loop node, and break our hit results for each to allow us to get the actor that we hit. From here, we want to perform a test against our first criteria, the actor class that we want to look for. We want to allow ourselves a little leeway when searching for a class by allowing both specific and child classes. So let's perform a get class from the actor pin, and then a class is child of node, which will allow us to be sure that we're catching anyone that fits at the level we specify or below in the class hierarchy. What will we wire into the parent class? Our class-defined input, of course. For long wires like this, I like to use reroute nodes, just to keep everything clean. You don't need to do this at all, but you'll see me doing it a lot. Anyway, we're wiring that into the parent class pin here. Then the return value will be used for yet another branch. We're using that to filter out all of the pawns that we found that aren't the right class. The ones that will make the cut will then be added to the valid actor array, which we'll get a reference to now, using the ever-popular add unique node. Once all of this is done, let's perform another quick validity check by pulling a wire out from our completed pin in the for each loop and creating a branch. Then we'll grab the valid actor array, check its length, which tells us how many items are in the array, and say that it should not equal 0. If true, we'll leave the pin open and it will continue down the sequence. If false, we'll add another return node telling us that it found pawns, but none of them were derived from the class we specified. That wraps up the part of the function that gets the list of valid actors. Now we need to find the best match for our criteria in that list. Let's go back to our entry node and pull a wire out of the search criteria pin and get ourselves a switch on Enum node. This will automatically be called switch on eTarget criteria since we used it as the basis to create our node. Let's attach that to our then1 pin. As you can see, it has a list of all the criteria we specified when we created the enum before. A switch allows us to execute different logic based on which item is selected within the enum. For now, we're only going to concern ourselves with the closest pin. Let's plan a little bit before we go forward. We now have an array of actors that are the right actor class, and we need to get each of their distances and compare them individually. I'm going to do this through basically a simple draw and discard system. Think of it like drawing from a group of numbered cards and trying to find the card with the highest or lowest value. We don't know which the highest card is, so let's draw them in order, and we'll throw away cards that are lower than the one that we already have, and we'll exchange any higher cards we find for the one in our hand until we've got the highest. We can accomplish this pretty tidily. Let me show you how. First, let's set a low watermark, as it were, by using our max range as a baseline. Nothing is going to be further away, but it'll give us something to compare against. We'll create a float variable called bestValueFound and set it using our max range. Then we'll grab our valid actor array, and for each item within, we'll get the actor's location. We'll also want the searching actor's location as a point of reference, so let's grab their capsule component and get its world location as well. Now let's subtract the two and get the vector length. This returns a float saying what the difference is when subtracting the x, y, and z values of both vectors. From the loop body, we'll use a compare float, grabbing the new vector length and comparing it with our best value found. You'll notice the compare float node has three outputs: greater than, equal, and less than. We only care about shorter distances, so we want the smallest float, so we'll just ignore results that are greater than or equal to our current float. If something is less than, however, that'll be used to set the best value found, and also an actor reference variable which we'll call bestFound. This will be the actor reference that we'll use to output our best target. This will go through each object, trading up until it gets to the shortest float, and therefore the actor that best fits our criteria. After it's gotten all the way through our array, we're almost done. We'll perform one last validity check with an isValid node, wiring in our best found. Technically, this should never be invalid since we've already confirmed that our array had at least one entry, but it never hurts to be thorough. If the actor is valid, we'll set a bool which we'll call exists. If it's not valid, we'll set it as false. Then we'll wire the best found and create a new exists reference variable to wire into the return node. And that's our getBestTarget function, filtered to find the closest actor. We don't actually have any stats for our actors yet, so highest and lowest health, for example, won't really work yet, so we can just compile and test this part out and worry about following up with additional functionality later. We could have made this filter by closest always, but this way we can create a more versatile function. We always want versatility if we can get it. So we'll compile, and you could ignore the execution path that doesn't end with a return node warnings. That's expected at the moment. Now let's get the functionality actually working. We're going to want to go back to our AI NPC blueprint and add a new event. I generally advise against executing anything on the tick, as anything wired into event tick is constantly executing and wasting computing resources, but let's just be sloppy for purposes of testing and wire out our getBestTarget node. As you can see, it's got all the inputs that we defined as well as a self-reference. The way that we have it set up, we can use our drop-down menus and float input here to define all of our criteria. Then we'll wire out a branch node to make sure that we aren't getting any null references, and for the purposes of debugging, we'll do a quick and dirty print to the debug log with the name of the actor we got with our best target function. We'll use a getDisplayName node wired into a printString node. Of course, we'll need a few actors to check against, so let's go to our map and drop a few actors down on the ground for our actor to walk past while patrolling. Groovy. Now let's test. As you can see, there's a massive cascade of blue text telling us who is closest to our patrolling NPC. The next step will be making sure that our NPC can see the actor they're looking for, but that can wait until next time. Until then, thank you very much for watching, and I hope to see you again soon. Take care.